Good morning, everyone, and welcome back to our Water Basic Chemistry. My name is Matt Tomlinson. I'm with Eagles Environmental Support Division, and just going to go through some housekeeping slides to help you with your navigating experience. This is Chemistry Session Part 1B, the second session in the series. I want to remind all of our attendees that all lines are muted during the webinar. We are also recording this webinar session, and you will be provided a follow-up email that will include a link to this recording for this session. You have a couple of different ways that you can interact with our instructor today. You can do that using the Q&A function or Q&A button located on your Zoom toolbar, or you can also use the raised hand function, and we can unmute your mic and you can ask a question live. Some of you are taking this training for continuing education credits, and just want to remind you, in order to be eligible for CECs, you must be logged in as yourself. You must attend the entire presentation, and then you must answer the poll questions that we will be conducting during this webinar session. So we'll have one momentarily, one somewhere in the middle, and then one at the conclusion of the presentation. So these poll questions are a way that we document your participation in the webinar. We do generate closeout reports so we can see who answered the questions, what time those questions were answered, and etc. So with that, I'm going to turn it over to our presenter today, or our instructor, is Scott Schmidt with the Drinking Water and Environmental Health Division. So Scott, I'm going to stop showing my screen and bring yours up. And I'm seeing your PowerPoint presentation.
Hi, everybody, and welcome back to day 2 of Chemistry Basics Part 1AB. So today we're going to be wrapping up at least the first quote-unquote session or half of this with picking up with ideas that we left off with yesterday, continuing them a little bit, and then moving into the molar masses and balancing of equations and so on and so forth, right? Because I will say the balancing of equations is something that has a certain knack to it. You know, once you get it kind of thing. So I thank everyone for being here. The first thing this morning with chemistry. If any of you, well, probably not. I'll see some of you maybe at Operator's Day after the fact, but I would only think that would be anyone local because this gets done at 11. So, all right. With that being said, I think we're okay to go ahead and start the poll question because I don't think anyone would complain if we got out, 10 or 15 minutes early. So with that being said, Matt, if you can go ahead and start the first poll question.
All right, so you should see the poll question up on your screen right now. And these are for our metrics. How many people are viewing this webinar on the device that you are logged in with? So if you can take a moment to answer that. This is the first poll question. If you happen to miss a poll question, we do not have the ability to go back and rerun poll questions. So that's kind of a part of this process. We're already up to 96%, so really good participation in the first poll. We had great participation yesterday too. I'd say almost everybody did good at answering it. If you do not need continuing education credits, then certainly you do not need to answer the polls. You can ignore those. All right, 100%. So I'm going to go ahead and end that. Take it away, Scott.
Okay, so yes, no, hold on a second. Let me get a little brighter for people. There we go. All right, so yesterday we left off with naming, and I just want to do a couple more naming compounds before we move on to the rest of the stuff, all right? So what we did yesterday was a little bit, I guess, reverse of this. If you remember, we did like the ones up here. So what I want to try to do is let's go ahead and have everyone do like 12 through 15, and then try to do, we'll just say 16 through 19 here, okay? This is that sheet that was at the very back last week, yesterday, that we were working on where we did the ones up here. So I want everyone to just try 12 through 15 and then try to write the chemical formulas with 6 through 19, okay? So with doing that, I will make things a little bit easier for you. This is the review sheet from yesterday. Make sure you find this and set this aside because we're definitely going to be using this again momentarily. So I will go ahead and I'll put the polyatomic ions here for everyone so that they can see them. So that with naming and trying to write out the names, it's more sensical. So you don't have to try to find that. So I'll give everyone like 10 minutes to start out with trying to go ahead and name and then write the compounds based off the name of those ones that we talked about. All right. So we'll give everyone 10 minutes to start the day with this, and then we will begin. That's why I said I wanted to pick up where we left off yesterday momentarily, and then we will move into the rest of the stuff. All right. All right, well, let's go ahead and get these out of the way, and then we will continue on, as they so to speak. Today is the day we're actually going to be doing some math too, just FYI. So if you don't have a calculator with you, highly recommend. I don't have mine with me, so I'm going to commit the mortal sin of using my cell phone. But the one that I recommend is a Texas Instruments. All right, and it goes by TI-30XIIS. They are like $12 on Amazon. I was just looking at them this morning. I have 2 or 3 of them. They're down in my truck. I forgot it in the parking lot. So I'm using the mortal sin of using my phone. Do not bring a cell phone to the certification exams in May 3rd, because if we catch you with a cell phone, you will fail. All right. So at any time, be sure to bring a non-programmable calculator. This is one I recommend. And yes, that is II, because that's what it is, X2S, but it's an II. All right. So with that being said, let's go ahead and name these. So I have sodium, because remember you always write, so this is a ionic because it's a metal and a non-metal, which this is a polyatomic ion. So I have sodium carbonate for the first one. And then you see here, this isn't a polyatomic ion, and it's 2 metals not bonded together. And S stands for sulfur. I mean, there's only one, you only have to write the sulfur. And then 4, chlorine. And it goes mono, di, tri, tetra. So it's tetrachloride. NF3, 2 nonmetals bonded together, and there's not a metal with it. So even if it was a polyatomic ion, it is not. So there's only one N, and N, if you use your periodic table, is nitrogen. 3 is tri. And then F stands for fluorine. And remember, on that, you drop the ene and add ide. So nitrogen trifluoride. And then KMNO4. This is a polyatomic ion here. And this is potassium. MnO4 is permanganate. Some of you, if you are limited treatment people, might actually use this. Potassium permanganate has also been used. It's used to recharge filters that have manganese removal in them, like green sand filters and such, in limited treatment schematics, but it can also be used in complete treatment for like zebra mussel control. And there's been research that's shown that potassium permanganate feeds at a raw water source not only work for zebra mussels, but it also helps with algae. For the fact that it's such an oxidizing part here, the O4, it does very similar reactions to what you see in ozone, where stuff is so oxidized that it kind of just burns it out. So it can be used for plankton and algae control too, is another thing. So I'm not saying run out and just add it to your plant. Obviously, you got to have studies and stuff done. Just telling you what that is a use for in the drinking water world here. All right. All right, sulfur dioxide. All right, so S for sulfur, dioxide. So it tells us O is oxygen, di means 2. All right. Now the next one is calcium, which is Ca, which is a +2. Phosphate, which is a polyatomic ion like this, has a -3 charge. And if you remember, you got to cross them. So the 3 comes here and the 2 goes there. So it's Ca3PO42. When it's outside the parentheses like this, that means it's 2 of everything in there, or you multiply everything by 2. So that means there's 8 oxygen and 2 phosphorus, okay, with that 2 here. Just so we're going to be talking about that later. So I just want to make sure we're aware of that. Chlorine dioxide. Has anyone in the water world heard of that? Because I'm assuming most of the people that are on this are complete treatment or limited treatment. And how about chlorine dioxide? Has anyone ever heard of that? chlorine dioxide is used as an alternative disinfection. It can be used. I don't know of anyone in Michigan who's using it. So you have the Cl for chlorine. You know, I could have zoomed this in a little bit. Sorry about that. You have the Cl for chlorine and the dioxide is O2. Yeah, so chlorine dioxide is something that is used as a disinfectant, but if it is, you have to start monitoring for chlorates. And the reason for that is chlorates are known to be a carcinogenic, okay? And they are monitored, but this is used sometimes, not necessarily Michigan, but like Texas uses it a lot. All right, the next one here is carbon tetrachloride. So I have carbon, which is C, tetra means 4, and then chlorine or chloride is Cl. So CCl4. Does that make sense? Yes? All right. Now, with that being said, enough of the naming.
Yeah, we do have a hand up, so
Okay.
we'll see if Anthony, we're going to allow you to talk. So if you want to unmute your mic, you can ask a question. So Anthony, we've unmuted your mic on our end. If you have a question, please feel free to ask it. All right, well, we're not getting a response. Oh, here we go. Oh, put his hand down, so go ahead.
Okay.
Sorry for the
Oh,
interruption.
that's fine. It is what it is, you know. All right. So, I wondered if he was going to ask more about the chlorine dioxide. Like I said, is used as an alternative disinfectant, and it's used because if areas have high organic loads within their water, chlorine dioxide is kind of like chloramines, where it doesn't react with the organics to form trihalomethanes and haloacetic acid, which are disinfection byproducts. And Texas has karst aquifers. And what that means is like basically if this is your well here, you know, and it's pumped down here, and this is your aquifer you're pumping out of, karst aquifers, because it's all limestone down there, what it means is that anytime they get rain event onto the ground, it like kind of cuts holes through the rocks, like how the Grand Canyon's sort of built, but by a river. But so how it works is there's like holes cut down to their aquifers. So it has direct runoff from the surface. So they have tons of organics in their aquifers or wells down in North Texas. And that's why they use chlorine dioxide. Nowhere in Michigan that I'm aware of yet uses it. Though a lot of secondary treatment is starting to pop up in hospitals and stuff like that. And some of them, for some reasons, are installing or have debated about installing chlorine dioxide, which is, it's a very complex treatment to add that. Actually, it isn't as easy as just adding, you know, bleach or whatever. So anyway, that's a different discussion for another day. So let's go ahead and move on. Yeah, we're done. Okay, now atomic mass. So I'm going to teach, we're moving down atomic masses, molar mass percentages, and blah, blah, blah. This is stuff that you're actually going to see on your exams, okay? So first off, with atomic masses, they are on the periodic table in each element. We mentioned them briefly yesterday. So on my periodic table, the atomic mass shows up at the bottom or the top typically. And it's important to know that the periodic table is how much an element weighs when we're talking about atomic mass, okay? It's how much it weighs, you know, just like we have a weight that's different for each one of us. The atomic mass for each atom is going to be different. And recall that the mass of an atom is in its nucleus, and it is all based on protons and neutrons within the nucleus, okay? The mass comes from the protons and the neutrons, okay? Everything on the periodic table is neutral state, and even if it is an ion, we don't change that because electrons' weight is so minute that we consider it kind of just like a wash. Does that make sense? So even if it is ionic, it still is considered the same weight that we see in the periodic table. The atomic weight that's on the periodic table also, it is where a lot of periodic tables go far beyond the second decimal point, but for us, we will only go to the second decimal point. And same with that for the calculations on your certification exam. On the math formula sheet that was dumped into the chat yesterday, I believe, it is on our website in like 4 different places. It has its own button. The math formula sheet has all of the elements listed on the back of it with the atomic symbol and with the weight. All right. That is the weight that we have used to calculate the stuff on the certification exams. So when you are looking for molar mass percentages or atomic weights, that's where you'll look, all right, to do the mathematics. All right. So with that being said, one last thing to keep in mind is the atomic weight is the average weight of all known isotopes. And if you remember, isotopes mean it's the same atom or element, it just has extra neutrons in the nucleus, right? So it's an averaged weight. So we're just assuming, you know, I know that's a horrible thing to say, but that's just to say, like, every human being weighs 150 pounds, right? Well, you know, it is what it is. So that's what we do with carbon is we're using the average of the most commonly known isotopes, you know, with them constantly at super colliders where they're just ramming, you know, atoms into other atoms, because that's what a super collider essentially is. They're taking, you know, gold and, you know, aluminum and ramming them into each other, and it makes different stuff. Well, there might be other isotopes out there, but they only exist for a few seconds and poof, they're gone. Okay. And that on the periodic table, when we were looking at it yesterday, maybe some of you noticed these numbers down here that are hollowed and they got these crazy names. Well, what these names are is where they were discovered or built or made or whatever. And 99% of them are from a super collider. And that's literally what it is it's like, you know, you put gold over here and you take, you know, whatever, you know, we just say it's iron this time. And we shoot it at like super high speeds and they hit each other and it becomes a bunch of these different crazy named ones right here. It becomes these, but they only exist for like the blip of a second. They have all these sensors to detect stuff like that. All right. So these ones we will never mess with because they don't exist in nature. They're created by man and they go poof as soon as they're created within just milliseconds. So, all right. So we're looking at like oxygen here. You can see that with oxygen, it says 15.9. Oh, I just wrote all over it. Oops. It says 15.99. We only want to go to the 2 decimal places. Well, what I just crossed off, I probably can't see it either. No. It's rounded to 16. Oxygen is one that's rounded to 16, just so we're aware. All right. So raw oxygen, I will be referring to as 16, just so we're clear on that. All right. So let's go back and actually do it. So that's the first things we need to understand. All right. So being that, I gotta start that. The learning objective here is how to determine the atomic or molar mass, the molecular mass calculations. All right. This is the very first thing we have to do to understand how molar mass percentages work. All right. So molecular mass is not that hard, but I'd like to show you how we do it. The first thing is A, knowing how to write the chemical based on the name, or B, how to determine its name just so you have an idea of what it is based on the chemical formula. You cannot do a molecular mass without a proper chemical formula written out. Now do you see why we talked about naming and stuff? It wasn't because I wanted to blow my hot breath. It was because it was for a good reason. All right, so water. I'm going to switch to this and do this on the calculator, or not calculator. I got some blank paper today. I was thinking ahead of the game. So we're going to be dealing with, make that clear for everybody. We're going to be dealing with H2O. Does everyone agree with that? This is water. Okay. So I know that H2O, this subscript means that there's 2 of these, right? H is hydrogen, first off, all right? H is hydrogen. and O is oxygen. So we can put the abbreviations like this. Now, how many of each of these do we have? So I have 1, 2. That subscript tells me I have 2 of the thing before it, which is I have 2 atoms and I have 1 atom of oxygen. Okay, now that you know how many you have and you've written that down, now you're going to go find the atomic weight of them. Okay, so the atomic weight of them, again, is on the periodic table. And you probably can't see hydrogens here, so you're going to need your periodic table. I'm on focus. So you can see it's 1.007. So this 2 decimal place is 1.01, okay? So this is going to be times by 1.01. And then we already talked about oxygen. Oxygen is 16, all right? So you then write your weight here. So this is 16 grams. So you do just like it says. 2 times 1.01. That's not that. 2.02 grams. And then the next thing you do here is 1 times 16 grams is 16 grams. Okay. Now what do you think we need to do to this? We need to add them up. So the atomic weight of water is 18.02 grams. This is the molecular weight. So the molecular weight of hydrogen is 18.02 grams. All right. And before we get ahead of ourselves, as you know, sometimes I have some chemists in here, sometimes I don't. But I know you're probably thinking, this is 18.02 grams per mole, right? That is a whole, that's next week, I think, right? That's the next session, so don't worry about any of that. We just want to know that water weighs 18.02 grams. Does that make sense? All right. That is known as the molecular mass or molecular weight of water. All right. So that's how that's done. So let me give you another one to try out. So hopefully you got your periodic table handy. All right, let's try CO2. All right, so I'll give everyone like 2 minutes to figure this out. Give it a try, and then we'll move forward and do it together, and then we'll continue on. All right, so we have CO2. So C is carbon. This is oxygen, right? Luckily, we didn't have to go look up oxygen, but I have one atom and I have two atoms here. So my carbon, when I look it up, comes out to 12.01. And oxygen is 16 grams from earlier. So this is 32 and this is 12.01. So I add those together and I get 44.01 grams. That's not so bad, is it? That seems pretty straightforward. The molecular mass isn't like some crazy hard thing here. All right. So oh, I didn't even realize that was in it. Okay, well, guess you guys had the answer for that one. Okay, let's do a little bit harder one than these, okay? And what I mean by that is let's go back to the paper because, whatever, you got the answers here on how to do them. Let me give you some that are harder and explain how they work, all right? Because, one we've seen a couple times now is this one. Ca3PO4 2. All right. So with this one, we have calcium phosphate is the name of it. But all right, so let's go ahead and break this down. This is how I always break these down. Ca is calcium. I have 3 atoms, right? I have P. How many atoms of P do I have? Remember what I told you a little bit earlier, that this parentheses, the 2 on the outside means times 2 of everything inside. Does that make sense? So with phosphorus, there should be 2 atoms because it's there. Even though there's not a thing there, it is a 1. Okay, that's what it means. When it's standalone, it means 1. So 1 times 2 is 2. O, which is oxygen, has 4 times 2, so it has 8 atoms. Okay, so now I'm going to go in my periodic table. Ca is in group 2. And well, I guess if I go to 2 decimal places, this thing weighs, oh, we got to multiply that. It weighs 40.08. Phosphorus is 30.97. And oxygen is 16. 32 for 120. I can do that one in my head. The rest of them I gotta get a calculator. I'm not that good. All right, calculator. So 3 times 40.08 equals 120.24 grams. 2 times 30.97 is 61.94 grams. Now we got to add all those together, right, to get the molecular mass. So this is 120.24 plus. So this thing weighs 310.18 grams. So as you can see, the bigger the molecule gets, the more it weighs. That makes sense, doesn't it? So with that being said, let me give you all a couple of examples to do on your own here to give it a try. I guess I can walk through one more. Let me think of a good one. Yeah, that's a good one. If anyone could type in the chat what that is as a question in like 30 seconds, what the name of that is, I'd be impressed. Oh, they're looking. They gotta look at trying to figure it out. Oh, what we get? We get an answer. Ammonia for yeah, okay. I guess that doesn't surprise me. Good job, Forrest. That is correct. All right. It is ammonium hydroxide. It's a combination of the two polyatomic ions. All right. So I want everyone to do the atomic weight of this thing. I'll give you like 2 minutes to try this out. Give me the molecular mass of ammonium hydroxide. All right. So here I have N, which I got one atom. Hydrogen you can do is combined, even though they're separated here, have 4 plus 1 is 5. So this is hydrogen, 5 atoms. And oxygen, we have 1 atom, okay? Okay, so times. This is 1.01 grams, 16 grams, and 14.01. Okay, now I look to check. Yes. Yes, I'm that big of a nerd that I have some of these memorized. Okay. So this is 14.01. This is 5.05. And this is 16. Add those together. 31.05. Yeah, 31. 45.06. 45.06. I don't need my calculator while I'm grabbing that thing. 45.06. All right. I think now, if we can, you guys should be, hold on, let me look at this stuff. Here's this. Oh boy. I guess that's it. All right. I want you guys to do a couple more for me on your own. I'll write them out on paper here. As I just realized I kind of hosed myself with this. I want to do C6H12O6, and we'll say one more down here of Mg. Yep, go ahead.
You're getting corrected on your last math calculation. 35.06.
Oh yeah, that's not 31, that's 21. Oh, okay. My bad. It was 35.06, you're right. Just shows, see? Use a calculator. See, I was trying to do that in my head and I messed it up. All right, and then, okay, I'll make sure that I do these ones correct for you, okay? All right, so go ahead and do these two. I'll give everyone like 5 minutes to do these, and then we'll come back, do them together, and I promise I'll use a calculator this time. All right. How we doing? We done? All right. So we're going to do this and then we're going to move on. All right. So 6 atoms of carbon. H has 12 atoms. And does anyone know what this is? Out of curiosity, what this compound is? C6H12O6. Anyone know? Forrest, out of curiosity? Without Googling it? No, maybe. All right, so anyway, this is 12.01 grams. This is 1.01 grams, and this is 16 grams. So we're gonna have, this is gonna be 1212, 3296 grams. And then I gotta do that one. 6 times 12 is 72. I think. I'm not trusting myself now. All right, 72.06. By the way, this is glucose, which is a sugar that is in your body, glucose. All right, so 72.06 plus 12.12 plus 96. All right, there. I know I got this one right because I can't type into a calculator. All right, so 180.18 grams. That's the molecular weight of that. And then we have HCO3, MgHCO3-2. All right, or magnesium bicarbonate is the name of this one. All right, so we have Mg, we have H, we have C, we have O. We have one atom of this. Do you all agree? There's only one, so it's one, not atoms, one atom. H, we have parentheses again, we have the 2, so we have 2 times 1, so we have 2 atoms of this. Carbon, there's only 1, but you got to multiply it by the 2. 2 atoms. Then oxygen, 3 times 2 is 6 atoms. So we have 16, 12.01, 1.01, and 23, 24, 24.31. It's in group 2, it's just above calcium. 24.31. Okay. These are all grams. Again, 3264.96 grams here. This is 24.02 grams, 2.02 grams, and 24.31 grams. Got to add all these together. (96 plus 24.2 plus). All right, I got 146.335 grams. That's a horrible 35. All right, so that's what we got for molecular weights. So why did we spend so much time on this? Okay, the reason I want to ensure that you know how to do them, right? We've done 6 of them now. Molecular mass directly feeds into what we're about to talk about, all right? And this is another concept that is on your thing. So we've done these, right? These are examples. So we all know how to do this now. All right. So the other thing about this that we like to talk about is we like to talk about molar mass percentages now, okay? And what is molar mass percentage? So what molar mass percentage is we're looking at the molecule itself, and molecule is another word for compound, just FYI. So here we have calcium carbonate, all right? So as you can see, we're finding a molecular weight of it, and we get 100.09 grams, right? A lot of people like to just say it's 100 grams, right, as a shortcut, but we're doing 2 decimal places, so it's 100.09. So what molar mass is if you think of, you know, like water, right? It looked like Mickey Mouse when we looked at it in 3 dimensions. Well, we agree that in water, there are 3 different things bound together. There's 1 oxygen and 2 hydrogen, right? Just kind of like here, you can see there's 1 calcium, 1 carbon, and 3 oxygens, which is what we were just doing and why we were breaking it down for the molecular weight. Now, here in this question, it says, what percentage of molecular mass does carbon represent in calcium? So first, in order to do that, you need to do what I like to call part of the whole, okay? So you're going to look back at your molecular weight calculation here, right? We know the whole thing is 100.09. Oops, go back. We know that the whole thing is 100.09. So that's the whole thing. And on a fraction, so when you think of a fraction really is part of the whole. All right. The part of is whatever you're asking about, and the whole is whatever the whole thing is. Does that make sense? So we're asking what percent of calcium carbonate is carbon. So this is the part of calcium carbonate's the whole thing. So what we're looking at is we go back to our calculation. We found that 12.01 grams of the whole thing is only for carbon. That goes over the whole weight of calcium carbonate, okay? Which gives you a decimal of 0.12, but to get that to percent, you have to multiply it by 100, and that will give you the percent. So, like water, here's another example. The hydrogen is 2 atoms, the oxygen is 1. What percentage of the molecular mass does oxygen represent in water? So we do it. We got 2 atoms, so times 1.01, which is 2.02. 1 atom of oxygen is 16. You add them together, you get 18.02. So we're asking the part of the whole, and the part of is oxygen up here at 16, and the whole thing is 18.02. So how do we do this stuff? Okay, so let's go ahead and practice these ones. All right, so let's go to our camera. So it's sulfur and potassium permanganate. Okay, so aluminum sulfate is Al. Oh boy, hold on. SO4 is -2. Aluminum is a +3. Okay. All right, let me go into the camera here. I'm not in the water industry, so I don't know this right off the top of my head. This is +3. SO4 is a -2, so Al2SO4 3. That's crap. Hold on. Al2SO4 3. Okay, that's better. So that's aluminum sulfate. So we want to know what percent of sulfur. Okay, this is what percent of sulfur in the compound. Okay, so I want everyone to do, you know what, I'll do this one and then we'll go, let you do the next one. All right, so this is just like we've been doing. Al, I have 2 atoms. Sulfur, I have 1 times 3 is 3 atoms. And oxygen, I have 4 times 3 is 12 atoms. Okay. Aluminum's weight is Al is 26.98 grams. Sulfur is 32.07 grams. Oxygen is 16 grams. This is non-hydrated aluminum sulfate, just FYI, because everyone's going to be, the aluminum sulfate I use in treatment is 598 grams or whatever, or something like that. 594, I think. Excuse me. This is going to be 53.96 grams. 90. can't. I don't want to try to do that in my head. 192 grams. All right, so we got to add these all up. All you're doing with molar mass percents is you find the atomic mass. That's step one, just like we've done. We've done 6 of them, right? And at this point, everyone should be pros at it. 96.21 plus 53.96. Yeah, 342.17 grams. Let me do that just to make sure. Okay. So this is how much this whole thing weighs, okay? So the part of the whole thing we're looking for is sulfur, which is this one. So we're going to take 96.21, divide it by 342.17, and this will give you your percent or your decimal first. 96.21 divided by 342.17. This equals 0.28. Well, how do you get 0.28 to a percent? You can multiply it by 100, or you can do what I do is you just move the decimal 2 places to the right, which is 28%. So sulfur is 28% of aluminum sulfate. Okay, does that make sense? So that's how you do molar mass percent. You do the atomic mass like we have, and then you find how much sulfur is at the end here, and then divide it by the whole thing. And that gives you a decimal that you then just have to convert to a percent. Okay? So let me get another fresh piece of paper here. The next one was oxygen and potassium permanganate. Okay. What percent is oxygen in this compound? And I'll write it out for you. Potassium permanganate is KMnO4. All right, so I'm going to give everyone three minutes to go ahead and do this for the molar mass percent of this, and then we will go over it. We'll take our break, and then we will finish the last leg of our journey together. All right, how'd we do? All right, so K, Mn, O, yeah, 4, 1, and 1. Okay, so this is 16, which equals 64 grams. Mn is manganese, which happens to be right in the middle, and this is 54.94 grams. Okay, manganese. And then potassium's 20, nope, 39.1. Nope, 91. All right, so we have 39.1, 54.94. That's a 0. Add these together. All right, well, let me get my calculator out because not doing that twice in a day. 1 times 39. What am I doing? 39.1 plus 54.994 plus 64. So 158.04 grams. That's the total. What percent is oxygen? Well, oxygen is 64. So 64 divided by 158.04 gives me 0.40, which is 40%. So oxygen represents about 40% of potassium permanganate. Does that make sense? Yes, I hope so. All right, let's go ahead and do our 10-minute break. Be back here at 9:47, and then we'll pick up where we left off. And it will be balancing equations and learning how to do that, okay? So I'll see you all back in 10 minutes at 9:47. All right, we should all be coming back from our break right about now. I'm getting ready to go on into the second part of today. This is another thing that, let me get the PowerPoint pulled up here. Matt's going to be running another poll question, so everybody should be back here.
All right, well, you're bringing your screen up. I'm going to go ahead and launch the poll question. So we are curious, how many years of experience do you have in the drinking water and or wastewater profession?
Yeah, this is something I want to know. This would be curious to see. A lot of the old timers are starting to fade away, so we're starting to see, people from the 0 to 9 category. Those two, I wouldn't be shocked if they were the highest on this call.
All right, well, we got about 96% that have responded. We'll let this run another 15 seconds before we close it out. And surprisingly, it is the majority is in the 0 to 4 years.
Yeah, that's what I kind
And
of figured.
5 to 9 and 20 plus are pretty much neck and neck. All right, so I'm going to go ahead and close this out and share this so that everybody can see the results. Kind of interesting, the 10 to 14 years is just a small 4%.
And that's what's crazy, man. I fall into that category. I mean, I know I'm only 34, but I fall into that. And that's what I've been trying to tell people, because we even see that here at the state, just so you all know. In my division in drinking water, the drinking water division, if you look, majority of the people here have been like 6 years or less in our division. And it's like 70 some percent, like this is close to 60. And then the people that are in that 10 to 14 year range, like me. So I'm young, but I'm like the transition of, from like the old, because I worked with all the old timers that a lot of like Richard Benzie, Brock Howard, Pat Cook. I got even a little time with Eric Way when he was working at AWWA and stuff like that. Laura Tran. So like I worked with all these older people that had been here 40 plus years, Jan Blumker, Doug Pasco. And then, so I got to work with all of them for 2, 3, 4 years. And then there was like a weird transition where they all retired, and all the people that we've had since then, the 6 and under. So like, to be honest, in my division, that 4% thing is pretty dead on. I can only name in the 10-year mark, like me, there's only like 8 of us of 174 staff. So it's same thing with us. Like you have the older, still 15 plus, and then like 6 and lower. And at that 10-year mark, there's not very many in our division either, Matt. So there's a weird transition phase there for a few of us. So
All right.
okay, with that being said, let me go ahead and share my screen and we can continue on. So this, of everything we've covered for the last 2 days, not 3, like last couple days, this is probably going to be the hardest for people to understand. And I don't mean that contextually it's hard, but it's just there's so much to track, and there's kind of a, what's the right word I'm looking for here? There's a knack to doing it. It's something that takes practice. I do not expect anyone at the end of today to be absolutely perfect at this. So on the certification exams, we do ask how to balance. There is questions on how to balance reactions, or which of the following is a balanced reaction. How about that? Okay. So you got to have the tools in your toolbox, so to speak. It's not a lot of questions. It's, I'm not saying you're going to show up and your entire test is going to be chemistry, but there is a knack to it. And I will teach you a couple things that I have learned over the years of doing this, which it was my freshman year of high school I took this, so I was 14. So this was 20 years ago for me. I've been doing balancing equations for 20 years. So I have a little bit of experience with it. So I will teach you though, what I call the even odd trick. And it's something that I kind of developed on my own, but when we get to it, you'll understand what I'm talking about. Okay. So the learning objectives for this PowerPoint is to learn how to balance reactions. Okay. So if you're given a blank slate chemical reaction, I'm going to hope that with the stuff I teach you, you will understand how to do it. All right. So today we're going to be talking about a straightforward reaction. Okay. This is theoretical. And what I mean by theoretical is just we put stuff in, it reacts, we get stuff out of it, right? That's what I mean by a theoretical reaction. And what we're going to be talking about is we're going to be talking about the reactants first. And the reactants are the things that you are starting with, okay? On our chemical equation that we're going to be doing, the reactants are on the left side. So those are the ingredients or the chemicals, that atoms and elements that you add first. Those are going to be on the left side of the equation. Then everything on the right side will be the products. So the products are the chemicals and chemical compounds that are created when a chemical reaction occurs. Like after the reaction's done, that's what you get, okay? So this is the reaction of how water is formed. And as you can see, like I was talking about, the area to the left of the arrow here is considered the reactants. We're going to consider the arrow a lot like an equal sign, okay? It just, we use an arrow in chemical or in chemistry because it means the reaction only moves forward. It only goes to the right. Does that make sense? And the right side of the equation here are the products. You know, it's kind of funny that water is what it is given the way that water can be created. Hydrogen in pure form like this is considered a gas, or it is a gas. It's hydrogen is a gas, hydrogen gas. Oxygen in pure form is also a gas. Water is born of fire. That's what's so ironic about it. What do you use to put fires out? In general, we use water to put fires out, right? If I dump a gallon of water on a fire, it typically goes out. A wood fire, grease is spread, whatever. That's why I said generally. But the reaction of creating water is a very violent one. Hydrogen gas mixed with oxygen gas explodes. You mix them together and you give it a spark, it will explode. Both of those gases are explosive. So you give it a spark, boom, and then you're left with water. Isn't that ironic? Water is used to put out fires, but water is born from an explosion. It's like I said, it's very odd, but it is what it is. So with that being said, this chemical equation is unbalanced. So how do we balance a reaction? This is a blank slate reaction. It's not balanced, and we're going to have to put what we call coefficients or numbers in it to balance it out. So we've already learned this, but when naming compounds and doing the molar mass percentages, we realize that these numbers, or the lack of numbers, like over here, there's no number on the water oxygen. That means that there's one. The numbers next to the hydrogen here, there's 2, then there's 2 oxygen right here, and then there's 2 hydrogen here. So just think about that. 2 hydrogen on this side, 2 oxygen, 2 hydrogen, 1 oxygen. That tells you it's not balanced because there's 1 here and 2 over there. So we need to first figure out how many atoms are on each side of the reaction. So in order to balance it, it's best for you to look at the equation as a whole and first, okay? Because looking for a starting point is kind of our thing, all right? So as you can see here on the left side, 2 atoms of hydrogen, 2 atoms of oxygen. And then over here on the product side, we got 2 hydrogen and 1 atom of oxygen. So we can tell that this isn't balanced, right? I mean, look at the numbers. The numbers don't lie. There's 2 and 2, so they're unbalanced. So in order to balance them, we need to add coefficients to them, all right? And what I mean by adding a coefficient is you add numbers in front of the compounds or chemicals. What that number means is multiply everything over here, okay? So in order to balance the fact that we only had one oxygen over here, we need to put 2 to make so that it balances with 2. So we put a 2 in front of water. And what that means is it's 2 times the 2 here, which gives me 4. See, we got 4 atoms here now of hydrogen on the right. And then 2 times 1 gives me 2 of oxygen, okay? Do you see that? Now, being I go back to the reactant side, I only have 2 hydrogens here, and I have 4 on the right. So how do I balance that thing out? Well, do I add a coefficient to this side now? Absolutely, you do. So, oh, I never changed that. Hold on a second, I messed up. Wait. It's supposed to be that way. Hold on, I'm dumb. Those are unbalanced, but now if we put a coefficient of 2 there, the 2 times the 2 here will make this 4 hydrogen atoms over here. You'll have 4 and 2, and you'd have 4 and 2. So the 4 on the reactant side with that 2 makes it now a balanced equation. As you can see, we redo the numbers on each side. 4 atoms of hydrogen and 2 on the reactants. On the product side, we have 4 hydrogens and 2 atoms. Now everyone's looking at that going, well, that didn't seem that hard. Well, the thing about balancing reactions is it doesn't seem that hard, but it truly is. And the reason I say that it is truly harder than it looks is for the fact that you have to, the reactions are much bigger than this. They involve much more stuff, okay? And we're going to work on a few more of these because I want to teach you some of the best practices for doing this, okay? First, with writing a complete chemical equation out completely, make sure to indicate the reactants and the products. The reactants for us are always on the left and the products are always on the right. It is best to determine the number of atoms on each side. I'm not saying you have to write it out, but it's good to kind of recollect, look at it. Determine which ones are unbalanced, add coefficients as needed, and there are compounds with polyatomic ions in them, remember, those great big grouped ions. And it's best to treat those as a singular unit. And then there's one other thing I like to teach, and it is what I call the even and odd rule. Okay, so we're going to be spending the next 40-ish minutes, 45-ish minutes, going over how to do these, and I will teach you rules. Okay, so we're going to be spending about 45 minutes on balancing chemical reactions, and I might even have you do a couple more mass percents and stuff here and there. Okay, so let me get out my sheet. I really wish I had a regular pen, because this thing bleeds through everything. And I didn't have. All right. So anyway, let's get out of this. And not a slideshow. Go to the camera. Okay. So first off, I want everyone to take a couple minutes to find this equation sheet. All right. And then on the back side of it, there's more chemical balance reactions here. Okay. So if we can find this sheet, and while you guys take a couple minutes, I'm gonna go get a pen real quick. All right, I'm here. Let's High Forest. Oh. All right, so I got a pen. Great success. Our sister agency, sort of sister agency, we have some things in common, is DNR. So anyone who's a hunter or fisherman, I'm actually on the DNR side of our building, and it's the CO level. So I just a CO or conservation officer. The guy who checks your fishing licenses just gave me a pen. Okay, so let's start with number 1 here, and I'm going to teach you guys how to do this. Okay, so first off, you see what I like to identify is looking for polyatomic ions. This is a very strange pen, but okay. So here we have polyatomic ions, sulfate, and you see that we have them on both sides, okay? Being that it's not split up, because sometimes the polyatomic ions get broke apart depending on the chemical reaction. But in this case, they don't. So what I'm going to recommend is you treat these as an individual unit, okay? And then we can see iron here has 2, iron here has 2, okay? So hydrogen here has H2 and H2 there. So what I recommend we start with is we're going to start with the iron right up front. All right. And you can see I have 2 iron here. I have 2 iron there. So I'm going to go ahead and I'm going to put a 2 on this iron here. So I put a 2 there and my iron is now balanced. Okay. Now I look at my sulfates. I have how many sulfates over here? Treat it as a whole unit because it's together. I have 3. Typically what I do is I'll work from here. I go iron, iron. All right. And this gets at the rule that I like to call the even odd rule. This was the odd number. This was the even number, right? So what you need to do with the even odd rule is you find what number you put in front that makes them both even. Does that make sense? Well, this one's 2, this one's 1. So if I put a 2 there, it makes it even. So now they're both even. That's the even odd rule. And here, now that the iron is balanced, I look at sulfate, I have 3, 1, 2, 3 because of this. So how do I get 3 over here? Well, put a 3 there. So now if you think about it, iron's balanced, sulfate's balanced. Now look at my H2. How many H2s do I have here? Hydrogens. I have 3 times 2 is 6. How many do I have over here? 2. Well, how do I get this to 6? Multiply it by 3. So you put a 3 there. That is fully balanced now. Does that make sense? I hope so, yes. Okay. We treat the polyatomic ions as 1, okay? And then I'm going to teach you another trick. It goes back to the even odd rule here with this next one, okay? This is known as a combustion reaction. CH4 is methane. That is what your furnace burns if you have natural gas, just FYI. Okay, so here on this left side are reactants. So here's our products. Now this one gets to, there's a trick to doing these reactions. As they get bigger, they get harder. But I have discovered the trick to these. All right, the trick to these is what you need to do is we need to make, because if you look, hydrogens are even over here. Carbon is easily balanced based off this too. So the biggest thing you need to do is you need to balance your oxygens. So the oxygens on this side, because they are only 3, we need to get it to even number. Okay. So because this will always be an even number, it's O2. So whatever we multiply by this will always be an even number. So to be honest, this is the last thing you're going to balance in this kind of reaction. It's an even odd rule. This is the odd side. We need to make even for oxygen. This is always going to be an even number. This is the even odd rule. Does that make sense? Because if I could put 99 in there, it's still going to be 99 times 2, which makes it an even number, okay? It will always be an even number. So what I do with this is look at water, and figure out how to get rid of all the hydrogen or balance them and make this an even number for your oxygen, since this is only a 1, okay? Well, how many hydrogen do I have over here? I have 4. How many hydrogen do I have here? 2. So how do I get that to this to match this with oxygen changing to even? Does that make sense? Because if I times this by 3, let's just say I did, will 3 times 1 be an even number on the water? It will not. Okay. So if I times this by 2, I have 4 hydrogens. I have 4 hydrogens. So that is balanced. Okay. And that made this oxygen 2. So that's now an even number. So this now changes to 4 oxygen on this side. You don't have to write these down. I mean, I'm just doing it to show you all. So now that I have 2 plus 2, I have 4. I have 1 carbon. I have 1 carbon. So that's balanced. The only thing that's not balanced is my oxygen. I only have 2 here. So how do I get that to the even 4? I just put a 2. All right. Does everyone kind of see what the even odd trick and how it works? Okay. You look for your symbols that have the 2s on the sides, and you use them to balance your singles on the other side. Okay. So over here, I can already tell you that this one is going to be, I look at my hydrogens or my oxygens because I only have 1 here. I have 2 there. So I need to get this to an even number. That's the even odd rule. This is the odd. I need to get the oxygen here to an even number because this will always balance real easily like that, okay? So in order to do that, I put a 2 here. That's 2 oxygen, 2 oxygen. Now I go to hydrogen. I have 4. How many do I have over here? 1. So how do I get that to 4? And just like that, I balance that reaction because now look, 4 hydrogen, 4 hydrogen, 4 chlorines, 4 chlorines, and then silicon, 1, 1. Just like that. All right, so let's go ahead and now that I've showed you a few of these, why don't you all try 4, 5, and 6 here? And I'll give you like 5 or 6 minutes to go over we'll give you 6 minutes for these 3, and then we'll go over them together, okay? So 4, 5, and 6 on this sheet. All right, how do we do? I just realized that number 5 is actually really hard. So if you didn't number 2, if you couldn't get number 5, don't be discouraged. I just realized that that one's really hard. After I set you up, excuse me, to it, I'm looking at it going, it took me a second to figure it out, okay? So anyway, AgI, which is silver iodide, sodium sulfide, silver sulfide, and then sodium iodide on the other side here. So I'm going to just go ahead and kind of look what we got going on here. I got Ag1 and 2, I11, S11, and A2. All right, so I see how to solve this in 2 seconds. So I have Ag with 1 over here, and I need 2 of them, correct? So put a 2 there. So 2, 2. Now look at iodide. That is what's connected. That comes over here. Well, I have 2 on one side, and I only have 1 over here, so I need to put a 2 there. Okay. Now look at sodium. I have 1. No, I have 2 because I multiplied by 2. So 2, 2. S, there's 1 sulfur, there's 1 sulfur over here. So I am done with that one. Okay. So this next one's hard. All right. This one's not as easy. Does anyone think they got this one? Can someone write me in the question thing if they think they got it? And I'll tell you if you did or not. Nobody? Just write the numbers like 4, 5, whatever. No? Okay, yeah, well, this one's hard. All right. So we got someone. Who is it? Yeah, good job. Well, 4, 5. Yeah, that's right. Good job, Kanoya. I probably butchering it. I think it's Kanoya, but I'm sorry if I butchered it. Yeah, that. All right. So anyway, let me show you. So this one's a little tricky because we have O2, which remember, this is always going to be even. Oh, I did butcher it. Yeah. All right. So this is always going to be even, right? But the problem that we have over here is we have 1 and 1, and it is even. But the problem is anytime I try to balance anything else, it's going to be an odd number over here. So like H3, right? H2 and H3, sometimes you can multiply those two together to get your lowest number, correct? So which would mean 6 hydrogen. So if I put a 2 there, it would give me 6 here, which would put a 3 here, which means this oxygen will always be 3. And it would be wrong because there's 2 nitrogen, 2, so it'd be 5 oxygen. So what you have to do is you have to play a balancing game on this one of getting this H3 to an even number so that this will be an even number, but the oxygen here will always be an even number too. So the next number up from 6 to make this even would be, it's got to be a factor of 3 because 3 times 3 is 9. So that wouldn't work. You see what I'm saying? 1 times 3 is 3. So that's odd. 6 is even. The next even number of multiplying things by 3 is 3 times 4. So I'm going to go ahead and put a 4 there. And that's going to give me 12 hydrogens here. Okay. That 4 gives me 4 times 3 is 12. How do I get 12 hydrogens over here? I put a 6. So how many oxygens does that leave me here then? That leaves me with 6. Over here, I only have 1. So that's 7. But I have nitrogens over here I need to balance, which is 4. Does everyone agree with me? 4N, 4N. So I add a 4 to give it that. Now look, I have 4 oxygen here and 6 here, which gives me a total of 10. How do I get 2 to 10? Multiply by 5. Yeah, that was a complex one. So if you didn't get that one, I won't be 4 plus 6, 2, 1, 2. Yeah, that wouldn't, just so you know, that wouldn't work. 2, 1, 2, 3. Because that will only give you the 1 oxygen here. 2, you got to go up to the next factor set, which is getting this to 12, all right? That one was hard. So I admit, after I gave the, I said 2, 4, 5, and 6, I kind of looked at it and went, oh boy, that's a hard one. Okay, so anyway, Fe3, so ferric, iron 6, I know, iron 3, no, 6, iron 6, oxide, carbon monoxide, iron plus carbon dioxide. Okay. So over here, we have 4 on this side. We have 2 over here. But if I put a 2, that's going to give me 2 carbons, which will give me that same odd thing that I was dealing with over here. Now, so, all right. The next step up for 4 to be even would be 8, right? Which means 2 of these and 2 of those. And get 2 there puts me at 4, which that won't work either. All right. So it's one of those guess and check things. You kind of got to keep looking at it. All right. So that would be 6. If I put a 2 there, put a 4 there, that puts that at 10. I put a 4 there, that puts that at 8. Yeah, this one's a pain in the butt to balance too. Honestly, I gave you guys a bunch of hard ones. Now that I'm looking at these. All right, so 4, 2. Am I overthinking this? No, I'm definitely not overthinking this. But 3, 6. Yeah, this one's hard. Would someone already do it? Or did you guys didn't cheat, did you? 2, 2, 2, 4. 2, 2. So that's 8, 4. Yeah, let me show you something about that. Yeah, I guess that's right, because that would be 2, 6. All right, so they got 2, 2, 2, and 4. And I don't know why, but I'm brain farting myself here. So 2 carbons, and that's why that doesn't work, because that gives you 4 carbons. That only gives you 2 there. So yeah, I didn't think so. Right. All right. So I thought I already did that in my head. All right. Not all right. 1, 3, 1, 3. 1, 3, 6, 3. Yeah, there it is. It's 3 and 3. I don't know why, but that one I was struggling with. See, and that's why using a pen sucks. I don't recommend it for this stuff. All right. 1 iron, 1 iron. We have 3, but if I have 3 here, that makes it 6. And then 1. Who gave me that answer, by the way? Steve O'Connor. Good job, Steve and Forrest and Tommy Sims. You guys are getting better at this crap than I am. Jeez, I'm rusty. It's been a few months. All right. All right. So good job. All right. So here it's 1 iron, 1 iron. And what we were doing is they balanced the oxygen to 6 on this side. And then they used the 2 over here to get it to the 6, which that was very clever. I don't know. I didn't think about that. But hey, you know, whatever. We can all only be human at some point. All right. How about everyone try number 9? And the reason for this one I want you to try is this has the polyatomic ions in it. We haven't only done one so far. So everyone go ahead and try number 9, and we'll see how we all do on number 9. All right, so I'll give a couple minutes on that, and then we'll go from there. All right. So number 9, let's go ahead and go over this. All right. So this one is plumb full of polyatomic ions. We have ammonium phosphate, lead nitrate, I guess more specifically lead 4 nitrate. Then this is 3, 4. This is lead 4 phosphate, and this is ammonium nitrate, okay, over here. So first off, I'm going to look, being that these are all, that's one thing to look for polyatomic ions first, is to make sure that they're the same, okay? Because like hydroxide usually doesn't stay together. If hydroxide's there, even though it's a polyatomic ion, it usually becomes CO2 and water on the other end or something like that, okay? So that's one thing to first notice, to make sure that they are the same, PO4, PO4, NH4, NH4, NO3, NO3, okay? Make sure that they are truly polyatomic ions. So the very first thing you could look at here is this one. So if I take ammonium, so I'm not going to write it, but ammonium, I need 3. So if I put a 3 over here, how many nitrates would that give me then? It gives me 3. This would be balanced, but it'll give me 3 nitrates. And then this is 4. Well, the lowest even number that those two typically have together is 12. So what you do is you'll take what you think should be 3, because you have 3, but you need 4, and multiply those together. Typically that gives you your lowest even number for those, which it does. So 3 times 4 is actually 12. So really I need 12 over here to balance this, okay? So I'm gonna go ahead and put 12. So how would I get this nitrate to 12 over here? I'm gonna have to multiply it by 3, right? 3 times 4 is 12. Well, that unbalances my other things. So now let's go back to my NH4 here, right? I have 12 over here now, and how many do I have over here? Well, I have 3. So how do you get 3 to 12? Multiply by 4. So I have 12 ammoniums, 12 ammoniums. I have 12 nitrate, 12 nitrate with the 3 times 4 here. Now I have 3 lead. And how many lead do I have over here? 3. Okay. I have 4 phosphates, and I have 4 phosphates. Okay. So I want to point something out. Let's see. I think I think of a chemical reaction that has something like that in it. I can't think of one off the top of my head. I really wish I could. I'm going to make a theoretical, all right, don't quote me on this. This is not a balanced reaction. I'm just coming up with something because I'm trying to think of one. NaO, Na2 oxide plus, yeah, let's do that. Plus, this will work, Rb2 oxide, okay? So we're not going to talk about this a ton, all right? I just want to point this out. You have rubidium here, and you have sodium here, okay? We didn't really talk about this, but as chemicals go down a series or a group, they become more reactive. Does that make sense? And if you recall my story about chemistry 1 yesterday, sodium, pure sodium, blows up or lights on fire just by the moisture within the air. That's how it is. So this rubidium is more reactive than sodium. Does that make sense? Okay. So in a chemical reaction, typically these things do what's called a replacement. They switch spots because it's based on reactive series, okay? Whatever is more reactive will switch spots with something else. Does that make sense? All right. Well, in this chemical equation, rubidium is more reactive than oxygen. Okay, this is a theoret. I don't even know if this would work, but I'm just going with it, okay? Because rubidium is more reactive, so in hindsight, they should switch partners, so to speak, kind of like this, okay? But at the same rate, it's going to give us the same stuff on the other end, right? It's going to give us sodium oxide and rubidium oxide too. But the reason I'm doing this is let's just say we balance this thing, right? We're going through doing the numbers and I got 4, 4, 4, and 4 to balance it, unquote. Just go with me, okay? This is an example. I couldn't think of anything off the top of my head other than this, all right? So sorry, but it does exist. Sometimes you balance reactions and you will notice that you get like 4, 4, 4, or you might get, something like 2, 2, like 2, 4, and 2, 4, okay? What do these have in common? And what I mean by that is, can you do math to those coefficients together with the same thing? 2 and 4 are both even numbers. That means you could divide them all by 2, doesn't it? So if I were to divide this by 2, this by 2, this by 2, and this by 2, if you can divide all the coefficients in a balanced equation by the same number, you can reduce them down. Does that make sense? And you should. Sometimes you just get so carried away with, the numbers are so big that you make them bigger than they need to be. So if everything can be divided by the same number, you need to do that and reduce them down, okay? Here we can't. Yeah, sure. This can be divided by 3, but you can't divide 4 by 3. Does that make sense? The only thing you can divide these all by is 1, and you're going to get the same answer you already have. So that doesn't work. But like in this example, if you have 2, 4, 2, 4, every one of these can be divided by 2 and reduced to like 1 and a 2. I know this is wrong, but I'm trying to prove my point to you or explain this to you. Because sometimes with balancing, you will sometimes run into this where you do it and you go, oh, wait a sec. Because someone had written in the comments, they wrote like 2224 or whatever. That was wrong, but yeah, like here, they wrote 22224. Well, the thing about that is you could have divided this by 2, this by 2, this by 2, so it'd have been 1112. I know the answer was wrong, but I'm trying to get to the point is if you do one of these and you look at them and they're all even numbers, well, you can divide them by 2. Or, if it's like, if they can all be divided by the same number without creating a decimal, then you have to do it to reduce it. Does that make sense to what I'm saying? All right, that's what I'm trying to get across here. I want to, oh, that's the answer to the last one. Yeah, okay. So that's why I wanted to point that out to you all right? That with balancing reactions, if you ever do it and you look at your numbers and you go, well, I feel like I can reduce those. You can reduce them, okay? If you can divide them by 2 or 3 or whatever, as long as it's the same number and you will not get a decimal, you need to do that because that means that it's not the empirical formula for you. It's just, it's balanced, but it's really big balanced. All right, so I want to make sure everyone knows what's going on. All right, so first off, what is the percent of, oh, let's come up with a good one. Sure, why not? What is the percent of, we'll go with nitrogen in PbNO3 4. All right, so I'm gonna give everyone a couple minutes to try this, and then I'll have you guys balance. I'm gonna give you one, I'm gonna give you one doozy of one, last one to balance too. So I'll give everyone like 3 minutes to try this out. I just want to make sure that everything that we've talked about has sank in, okay? All right. What is the percent of nitrogen in lead 4 nitrate? Okay, so PB, there's only one atom. Nitrogen, there is 4. Oxygen, there is 12, 3 times 4, okay? Atoms. So lead weighs a lot. Hold on. Right there. 207.2. This is 14.01, and this is 16. So this is 207.2. That is 56.04. I think that's 196, but I'm gonna double check. 2 times 16, 192. I'm gonna do that one too, just to make sure I didn't mess it up. Yep, okay. So now I add these together. So 56.04 plus 207.2 plus 192. 455.24 grams, okay? Now I said, what is the percent of nitrogen? So it's 56.04 divided by the part of over the whole. 56.04 divided by 455.24 gives us 0.12, 2 places to the right. So 12%. And then I wrote one more in there if I snuck it in on you. Maybe what I got. Oh, that's still from last time. Okay. And then I said name ZnOH2. Zn stands for zinc. This is ionic, metal versus and nonmetals. This is also a polyatomic ion. OH is hydroxide. So zinc hydroxide is that one. All right. So on the back of the one chemical sheet that we were balancing, okay? On the back, you see there's more formulas here. Okay, I said I'd give you one hard one and then we'll be done for the day, okay? And I want everyone to do or attempt to do number 9, okay? Combustion reactions, the bigger the molecules get, the bigger the numbers get, so they seem to be hard. And I don't know, has anyone noticed there's an answer key yet to cheat on? There is, so, but try to do it. Legitimately try to do this one. There is a trick to this I did sort of talk about, but try to do it if you can, okay? So everyone go ahead, give this a try, see what you can do, see if you can manage to do it, and then we'll go from there, okay? I'll show you the trick again and explain how combustion reactions work again. And by combustion, this is the type of reaction that occurs in like your motors and your furnace and all that stuff, so. All right, let's go ahead and go over this because this one's a bit of a mind bender, but there is a trick to combustion reactions. Okay, because I used to struggle with these, and then just because the numbers get so big, right? So trying to track all that crap in your head, if you're not writing it down, gets really big really quick. But it was last summer. Yeah, it was like August of last year. It dawned on me how to do these, and then I felt so dumb for not figuring it out before. But you know, that is life. So this is a combustion reaction. Again, we have the even odd numbers here, okay? But the thing about combustion reactions, a lot of times you will be able to get whatever number we put on the CO2 is always going to make that oxygen even, correct? Doesn't matter what it is because it's always oxygen. And then same here, whatever I put there is always going to be even. So the trick to this question, and being that this is only one carbon, regardless of how many ever carbons there are here, you can balance it easily. So if it's 29, all you gotta do is write 29 there, it's balanced. Does that make sense? So the only thing that you got to concern yourself actually is with the water, okay, to start. So you look here and look how many hydrogens you begin with, okay? And then you look at the water. So if I put 9 here, that's going to get me my 18, right? But is that oxygen going to have an even to it? No, 9 will not make this even. So go to the next step up. What's the only thing I can add to this in front? Well, one of them is 18. Well, 2 would make this 36, correct? Does everyone agree? Yes, 36. So 2 times 18 would be 36. How would I get this water to 36? 18. Would that 18 make this oxygen an even number? Absolutely, it does. Okay, so what you do is you just keep working on balancing hydrogens back and forth till this coefficient here would be an even number, because then it works with this. So I'm going to put 2 here and 18 there. Okay, because 2 times 18. Now, how many carbons do I need? I need 16, because I have 16. Does everyone agree with that? 16, 16. Well, that makes this 32, correct? And I think this is going to work out the way I was showing you earlier. Okay, so I have 36 on the water, and I have 16 here. Plus 16 is going to give me 52. No, that's 32. Stupid. Hold on. 32. 18 plus 32. Don't listen to me. 18 here. 16 times 2 is 32. 8's 40 is 50. Okay. So how do I get that oxygen to 50? 25. Now, if you could add right, it would have went faster, but that's my fault. Okay. Well, everybody, I appreciate you all for joining me again, all right, with this. I hope to see all of you next week, because this is a 6-session series, meaning if you paid, or a 4-session series, and the way you paid, it was for all of them, all right? So Matt, if you would, can you go ahead and queue up the last poll question so that we can get out of the way and get done,
Yep, we are
go to bed
launching
early.
that right now, and similar to yesterday, we'd like you to rate this session. So the poll is open. Go ahead and submit your answer.
Just remember, what we saw today will be on your certification exams if you take the F or D.
And so that's the drinking water side.
Yes, D as in limited treatment, not D as in D wastewater. I can't speak to their exams. I don't know what's on them, so I'm not even going to try to guess. So today we're going to be wrapping up at least the first quote unquote session or half of this, with picking up with ideas that we left off with yesterday, continuing them a little bit, and then moving into the molar masses and balancing of equations and so on and so forth, right? Because I will say the balancing of equations is something that has a certain knack to it. Once you get it kind of thing. So I thank everyone for being here. The first thing this morning with chemistry. If any of you, well, probably not. I'll see some of you maybe at Operator's Day after the fact, but I would only think that would be anyone local because this gets done at 11. So, all right. With that being said, I think we're okay to go ahead and start the poll question because I don't think anyone would complain if we got out, 10 or 15 minutes early. So with that being said, Matt, if you can go ahead and start the first poll question.
All right, so you should see the poll question up on your screen right now. And these are for our metrics. How many people are viewing this webinar on the device that you are logged in with? So if you can take a moment to answer that. This is the first poll question. If you happen to miss a poll question, we do not have the ability to go back and rerun poll questions. So that's kind of a part of this process. We're already up to 96%, so really good participation in the first poll. We had great participation yesterday too. I'd say almost everybody did good at answering it. If you do not need continuing education credits, then certainly you do not need to answer the polls. You can ignore those. All right, 100%. So I'm going to go ahead and end that. Take it away, Scott.
Okay, so yes, no, hold on a second. Let me get a little brighter for people. There we go. All right, so yesterday we left off with naming, and I just want to do a couple more naming compounds before we move on to the rest of stuff, right? So what we did yesterday was a little bit, I guess, reverse of this. If you remember, we did like the ones up here. So what I want to try to do is let's go ahead and have everyone do like 12 through 15. And then try to do, we'll just say 16 through 19 here, okay? This is that sheet that was at the very back last week, yesterday that we were working on where we did the ones up here. So I want everyone to just try 12 through 15 and then try to write the chemical formulas with 6 through 19, okay? So with doing that, I will make things a little bit easier for you. This is the review sheet from yesterday. Make sure you find this and set this aside because we're definitely going to be using this again momentarily. So I will go ahead and I'll put the polyatomic ions here for everyone so that they can see them. So that with naming and trying to write out the names, it's more sensical. So you don't have to try to find that. So I'll give everyone like 10 minutes to start out with trying to go ahead and name and then write the compounds based off the name of those ones that we talked about. All right. So we'll give everyone 10 minutes to start the day with this, and then we will begin. That's why I said I wanted to pick up where we left off yesterday momentarily, and then we will move into the rest of the stuff. All right. All right, well, let's go ahead and get these out of the way, and then we will continue on, as they so to speak. Today is the day we're actually going to be doing some math too, just FYI. So if you don't have a calculator with you, highly recommend. I don't have mine with me, so I'm going to commit the mortal sin of using my cell phone. But the one that I recommend is a Texas Instruments. All right, and it goes by TI-30XII. They are like $12 on Amazon. I was just looking at them this morning. I have 2 or 3 of them. They're down in my truck. I forgot it in the parking lot. So I'm using the mortal sin of using my phone. Do not bring a cell phone to the certification exams in May 3rd, because if we catch you with a cell phone, you will fail. All right. So at any time, be sure to bring a non-programmable calculator. This is one I recommend. And yes, that is II, because that's what it is, X2S, but it's an II. All right. So with that being said, let's go ahead and name these. So I have sodium, because remember, you always write, so this is a ionic because it's a metal and a non-metal, which this is a polyatomic ion. So I have sodium carbonate for the first one. And then you see here, this isn't a polyatomic ion, and it's 2 metals not bonded together. And S stands for sulfur. I mean, there's only one, you only have to write the sulfur. And then 4, chlorine. And it goes mono, di, tri, tetra. So it's tetrachloride. NF3, 2 nonmetals bonded together, and there's not a metal with it. So even if it was a polyatomic ion, it is not. So there's only one N, and N, if you used your periodic table, is nitrogen. 3 is tri. And then F stands for fluorine. And remember, on that, you drop the ene and add ide. So nitrogen trifluoride. And then KMNO4. This is a polyatomic ion here. And this is potassium. MnO4 is permanganate. Some of you, if you are limited treatment people, might actually use this. Potassium permanganate has also been used. It's used to recharge filters that have manganese removal in them, like green sand filters and such, in limited treatment schematics, but it can also be used in complete treatment for like zebra mussel control. And there's been research that's shown that potassium permanganate feeds at a raw water source not only work for zebra mussels, but it also helps with algae. For the fact that it's such an oxidizing part here, the O4, it does very similar reactions to what you see in ozone, where stuff is so oxidized that it kind of just burns it out. So it can be used for plankton and algae control too, is another thing. So I'm not saying run out and just add it to your plant. Obviously, you got to have studies and stuff done. Just telling you what that is a use for in the drinking water world here. All right, sulfur dioxide. All right, so S for sulfur, dioxide. So it tells us O is oxygen, di means 2. All right. Now the next one is calcium, which is Ca, which is a +2. Phosphate, which is a polyatomic ion like this, has a -3 charge. And if you remember, you got to cross them. So the 3 comes here and the 2 goes there. So it's Ca3PO42. When it's outside the parentheses like this, that means it's 2 of everything in there, or you multiply everything by 2. So that means there's 8 oxygen and 2 phosphorus, okay, with that 2 here. Just so we're going to be talking about that later. So I just want to make sure we're aware of that. Chlorine dioxide. Has anyone in the water world heard of that? Because I'm assuming most of the people that are on this are complete treatment or limited treatment. And how about chlorine dioxide? Has anyone ever heard of that? chlorine dioxide is used as an alternative disinfection. It can be used. I don't know of anyone in Michigan who's using it. So you have the Cl for chlorine. I could have zoomed this in a little bit. Sorry about that. You have the Cl for chlorine and the dioxide is O2. Yeah, so chlorine dioxide is something that is used as a disinfectant, but if it is, you have to start monitoring for chlorates. And the reason for that is chlorates are known to be a carcinogenic, okay? And they are monitored, but this is used sometimes, not necessarily Michigan, but like Texas uses it a lot. All right, the next one here is carbon tetrachloride. So I have carbon, which is C, tetra means 4, and then chlorine or chloride is Cl. So CCl4. Does that make sense? Yes? All right. Now, with that being said, enough of the naming.
Yeah, we do have a hand up, so
Okay.
we'll see if Anthony, we're going to allow you to talk. So if you want to unmute your mic, you can ask a question. So Anthony, we've unmuted your mic on our end. If you have a question, please feel free to ask it. All right, well, we're not getting a response. Oh, here we go. Oh, put his hand down. So go ahead.
Okay.
Sorry for the
Oh,
interruption.
that's fine. It is what it is, you know. All right. So, I wondered if he was going to ask more about the chlorine dioxide. Like I said, is used as an alternative disinfectant, and it's used because if areas have high organic loads within their water, chlorine dioxide is kind of like chloramines, where it doesn't react with the organics to form trihalomethanes and haloacetic acid, which are disinfection byproducts. And Texas has karst aquifers. And what that means is like basically if this is your well here, and it's pumped down here, and this is your aquifer you're pumping out of, karst aquifers, because it's all limestone down there, what it means is that anytime they get rain event onto the ground, it like kind of cuts holes through the rocks, like how the Grand Canyon's sort of built, but by a river. But so how it works is there's like holes cut down to their aquifers. So it has direct runoff from the surface. So they have tons of organics in their aquifers or wells down in North Texas. And that's why they use chlorine dioxide. Nowhere in Michigan that I'm aware of yet uses it. Though a lot of secondary treatment is starting to pop up in hospitals and stuff like that. And some of them, for some reasons, are installing or have debated about installing chlorine dioxide, which is, it's a very complex treatment to add that. Actually, it isn't as easy as just adding, bleach or whatever. So